Hello. So today I'm going to tell you about some concentration units. Some of this is review and some of this is new. The reason I'm doing this is because the next thing that we're going to be talking about in class, and we'll actually already have started to talk, well, I don't know if we'll start to talk about it by the time I make this, but that's all right. We're going to be talking about something called colligative properties of solutions. Actually, I believe we'll do this on Thursday. So I want you to be able to look at this video to prepare yourself for knowing how to deal with the different kinds of units that we're going to come across in that class. So these properties, these colligative properties, they depend on the amount of dissolved solute. So these are properties of liquids that change when you add a dissolved solute. And the thing about this is they depend on the amount, but not particularly on the identity. So the particles could be sodium ions or chloride ions or glucose or urea or ammonia or methanol. It doesn't matter what they are. What's really important is, how many particles you have dissolved. Okay, so we calculate concentration in different things. And some of the properties that change depends on concentration of the solutes in different units. So for example, these are the properties that change. So properties affected. So these are really liquid properties, things we've talked about at this point, affected by dissolved solutes. And those properties are vapor pressure. So if you add a solute, it lowers the vapor pressure above the liquid. I'll talk about that in class in more detail. But what I want to say about it now is it actually depends on the mole fraction of solute. Okay, so we need to be able to calculate mole fraction comfortably. Another property that changes is the boiling point or in the freezing point. The boiling point increases with dissolved solutes. Let's just call it solute. And the freezing point decreases with dissolved solutes. Okay? And how do they depend on the concentration of dissolved solute? Depends on the concentrations of the solutes in molality, which is a new unit for you that I'm going to go over in this video. And finally, there's something called osmotic pressure, which maybe you don't know too much or anything about at this point. It's given the symbol pi. And when you dissolve something, I'll explain what it is in class. It doesn't matter right now for now, but what matters is that this increases with dissolved solutes, and it depends on the concentration of solute in molarity units. Okay, so there's all these different units. And we also are familiar with things like percent by mass. That is another important concentration unit. And I'd like to just mention parts per million, which is a unit that's often used in environmental labs when they have very low concentrations. So it would be 0.00000 something in terms of percent, but maybe it would be 15 parts per million. So I'll talk about that a little bit too. And I want to call your attention to this activity 6. Okay, I'm going to give this as a special problem, so that's extra credit. I know we have a quiz coming up over the weekend, so I'll probably have the deadline be a little far out, like maybe a week from Thursday or something like that. But I'll post it. So, and what it does is it talks about a particular solution of sodium hydroxide and methanol, and it asks you to calculate all of these different things. And handily, it gives you all the equations for how to calculate these things. So I'm going to go on because I have my own example for you to do. And I'm going to talk about, let's suppose we have 6.25 grams of sodium chloride, and we dissolve it in water. Okay, and here's some, so when we dissolve it, let's dissolve it in 400 milliliters of water. Okay, but when we dissolve that sodium chloride in there, so we took 400 mils and added it to the 6.25 grams, but the volume of the solution is 402 milliliters. So we didn't make it up in a volumetric flask. We just added 400 milliliters to 6.25 grams of sodium chloride. So what I would like to do is, first of all, find something called the molality. And the molality, if you look over here, is the moles of solute, oh no, that's molarity, is the moles of solute per kilogram of solvent. So it's a little bit different than molarity. Let me write that down. Moles of solute per kilogram of solvent. Now, a kilogram of water is 1,000 grams. And if the solution, if you had a liter of solution, that's about a kilogram. So molality and molarity for water solutions are very close. And you'll see that in this calculation. But let's actually figure out what it is. So, so first we have to take and figure out the moles of the NaCl by converting our grams to moles using the molar mass, which is 58.44, which gives us 0.1069 moles of NaCl. Notice I've underlined the third significant figure, but I like to keep an extra figure until the end of my calculation. All right, so that's the moles. Now, 400 milliliters of water. And now I want to figure out how many kilograms that is. All right, well, you know, 400 milliliters, if you consider that the density is 1 gram per milliliter, then that would be 400 grams. But I'm going to say that this is 25 degrees C. And at 25 degrees C, the density of water is not exactly 1.00. It's actually 0.997 grams per milliliter. And I don't want to lose significant figures by calling this 1.0, because then I'd only be able to keep 2. But I have 3 sig figs here, and I want to keep all 3. So if you do this, it comes out to 398.8 grams, which I would round that to 399 if I were just stopping there. But I'm continuing with this calculation, because now what I have to do is I have to take my moles of the solute, which is 0.1069, and divide it by the kilograms of solvent, which is 398.8, again, underlining the third sig fig. And when I do my division, I get 0.268 is the molality. So that we call that 0.268 molal. That's the way we would say it. And we would write it as 0.268 with a little m. So that little m means molal. Right? Don't confuse it with mass, but we're not dealing with, this answer should not be a mass, so that shouldn't be a confusion. Okay, so that's the molality. What would the molarity be? Okay, so now we have to look back to the beginning of the problem, not that problem, the one I wrote. and I say that 6.25 grams of NaCl was dissolved in 400 milliliters of water, but then the final solution, the volume of the solution, was actually a little bigger than 400 because of adding the sodium chloride. It changed the volume a little. So, my solution was 402 milliliters, or 0.402 liters. So now molarity is moles over liters. It's actually the liters of solution. This is the kilograms of solvent. So it's slightly different. So this is 0.1069. That's the same. But now we're dividing by 0.402 liters. So look at this. This calculation here and this calculation here are almost the same in water. But if you had a solvent that had a significantly different density from 1 gram per milliliter, like a lot of alcohols, their densities are quite a bit lower, then this wouldn't look so similar. Okay, when you do the math here, it comes out to 0.266 molar. So you could see that these numbers are very close. And that's because the solvent is water. Okay. All right. So let's go on now and do the mole fraction. Mole fraction. Just make sure I'm recording this. Yeah, I think so. All right, so the mole fraction. So what we need to do is have the moles of each. We have basically sodium chloride and water. The mole fraction of sodium chloride is the moles of sodium chloride divided by the sum of the moles NaCl plus the moles of water. So we need to get the moles of both. So the moles of NaCl we already have. That's 0.1069. Okay, but we need the moles of water. So we have to know the grams of water. So it was 398.8 grams of water. And the molar mass is 18.016 grams per mole. Okay, I don't want to use fewer sig figs than the numbers here. So I want to use at least 3. So I used a few. And I end up with 20. Let me just do that again. Make sure I have the right answer there. 22.13. So I kept an extra sig fig there. And so now if I take this is 0.1069 divided by, you can see this is totally dominated by the water. Okay, so this comes out to 0.00481. Okay, and that is the mole fraction of NaCl. Whoa. Okay, now what if I want to find the mole fraction of the water? Yeah, I mean, I could take this number and divide it by the total, or I could just subtract from 1. And it comes out to 0.9952. That's the mole fraction of water. Sig figs are interesting here. I think wait a minute, I copied that wrong. It's 0.0481. No. It's 0.00481. Sorry. Okay. So it's 0.9952. Now I figured that, let's see. So I have 3 sig figs up here. And when I add these together, I get to keep 1 decimal place because this has the least. So that means that my denominator is actually going to have 3 sig figs. And so I'll have 3 sig figs in my answer. So when I subtract from 1, 1, 1, 2, I really get to keep all these figures. So 1 minus 0.00481 is 0.99519. That's bizarre, but that would be the answer for the mole fraction of water. Yeah, I mean, if you just kept 3 sig figs, that'd be fine with me. All right, so what about percent by mass? This is something that you did a lot in the copper lab, so I think you know how to do this. It's the percent of sodium chloride would be the mass of the NaCl divided by the total mass. So the mass of the NaCl is 6.25 grams, and we divide that by 398.8 plus 6.25, and that comes and multiply by 100, and that would be 1.54%. So this number here, before you multiply it by 100, is 0.0154. Now, so that means that if you took this solution and divided it into 100 different pieces, that 1.5 of them approximately would be sodium chloride. All right. Now, there's another thing which we call parts per million. And we often do this with very low concentration solutions. But to get a part per million, you do exactly the same thing as you do here. The mass rate of NaCl divided by the total mass. But instead of multiplying by 100 as you do for a percent, you multiply by a million. And so you would end up taking 0.0154 times 1 million, which is 10 to the 6th. And you'd get 0.0154 times 10 to the 6th, which would be 1,540 ppm. So if you divided the sample into 1 million parts, 15,400 of those parts would be sodium chloride. That's just because you divided it into a finer amount of parts, that you got more of them that was sodium chloride. But if you had something that was, say, you know, a very, very low concentration, like 0.0000034%, or but if that was the number instead of 0.0154, and then you multiplied it by a million, 1, 2, 3, 4, 5, so that would be 3.4 parts per million. If you express that as a percent, you know, the same number, it would be 0.00034%. And that's not a very, you know, that's not a very convenient number. You'd much rather say 3.4 parts per million than 0.00034%. So ppms are often used like in environmental labs, where toxic compounds have pretty relatively low concentrations. You'll see parts per million, parts per billion, even parts per trillion, okay, of toxic chemicals in drinking water and things like that. Thank goodness they're not higher than that. So, so that's just a little bit on concentration units, which maybe will help you with some of these colligative property calculations. Bye.